Okay, I hope I'm audible to all my students who are attending this practice lecture for the mathematical methods for economics course. In this particular practice lecture, I continue with the discussion of some problems based on the concept of homogeneous functions. In my last practice lecture based on functions in several variables, we had looked at some problems on finding the degree of homogeneity and verifying the Euler's theorem. In this particular practice lecture as well, we are going to look at some problems based on the concept of homogeneous functions for practice. So let's quickly start with this particular lecture. So I am just writing the main heading for completeness. We are looking at practice problems based on functions in several variables. Practice problems based on functions in several variables. Okay, so let's quickly look at the first question. Again, it's based on the concept of homogeneous functions. Okay, I have covered the concept of homogeneous functions in my theoretical lectures on comparative statics. Okay, so let's quickly look at this. Show that the function given by z, which is equal to a1 x to the power alpha 1 y to the power 1 minus alpha 1 plus a2 x to the power alpha 2 y to the power 1 minus alpha 2 is linearly homogeneous. Show that this function is linearly homogeneous. Also verify the Euler's theorem. Okay, so first of all, let us show that this function is linearly homogeneous. When I say linearly homogeneous, it means it's homogeneous of degree 1. So how do we show homogeneity? We all know from the past few lectures as well how to show homogeneity. Consider z, which is a function of x and y, which is given to us in the question as a1 x to the power alpha 1 y to the power 1 minus alpha 1 plus a2 x to the power alpha 2 y to the power 1 minus alpha. Now, if I look at f of lambda x lambda y, so wherever we have x, we put lambda x. Wherever we see y, just put lambda y. So it becomes a1 lambda x to the power alpha 1 lambda y to the power 1 minus alpha 1 plus a2 lambda x to the power alpha 2 lambda y to the power 1 minus alpha. So what do I get? This is a1 lambda to the power alpha 1 x to the power alpha 1 lambda to the power 1 minus alpha 1 y to the power 1 minus alpha 1 plus a2 lambda to the power alpha 2 x to the power alpha 2 lambda to the power 1 minus alpha 2 y to the power 1 minus alpha. Now lambda to the power alpha 1 and lambda to the power 1 minus alpha 1. The base is the same. I can add up the power. So it's alpha 1 plus 1 minus alpha 1, which is just 1. So I am left with lambda a1 x to the power alpha 1 y to the power 1 minus alpha. Basically, the powers got added up. So it's alpha 1 plus 1 minus alpha 1. This and this cancel. So I just get lambda to the power. Similarly, here also, lambda to the power alpha 2 and lambda to the power 1 minus alpha 2. So the base is the same. I can add up the powers. It's alpha 2 plus 1 minus alpha 2 times a2 x to the power alpha 2 y to the power 1 minus alpha 2. Again, alpha 2 minus alpha 2 cancel out. So what do I get? This is lambda a1 x to the power alpha 1 y to the power 1 minus alpha 1 plus lambda a2 x to the power alpha 2 y to the power 1 minus alpha, which I can further write it as taking lambda common. I get a1 x to the power alpha 1 y to the power 1 minus alpha 1 plus a2 x to the power alpha 2 y to the power 1 minus alpha 2. And if you look at this whole term, this is nothing but f of xy. This is f of xy. So what I've shown essentially is that f of lambda x lambda y is lambda times f of xy. Therefore, I can write that f of xy is homogeneous. It is homogeneous of degree 1. Or I can say it is linearly homogeneous. This is what we had to show. We had to show that f of xy is linearly homogeneous. I've shown that to all students. Now let's verify the Euler's theorem. So first of all, students should be able to recall the statement of the Euler's theorem. Now I'm erasing all this off. Hoping students have solved this along with me. Let us now verify the Euler's. So remember the statement of the Euler's theorem. I'm writing it again for clarity. Euler's theorem statement is as follows. X times del z by del x plus y times del z by del y should exactly be equal to z, where z is the function students can see on their screens. Now, can I find del z by del x quickly? So del z by del x is going to be the partial derivative of z with respect to x, treating y as a constant. If I calculate this, it's a1 alpha 1 x to the power alpha 1 minus 1 y to the power 1 minus alpha 1 plus a2 alpha 2 x to the power alpha 2 minus 1 y to the power 1 minus alpha. This is del z by del x. Can I multiply this by x? Because I need x times del z by del x. So x times del z by del x will be this whole expression multiplied by x. So if I multiply this by x, I get a1 alpha 1 x to the power alpha 1 minus 1 multiplied by x y to the power 1 minus alpha 1 plus a2 alpha 2 x to the power alpha 2 minus 1 again multiplied by x times y to the power 1 minus alpha. What I've done is, guys, I've multiplied del z by del x. This whole term I've multiplied by x. So this I can write as a1 alpha 1 x to the power alpha 1 minus 1 multiplied with x gives me x to the power alpha 1 y to the power 1 minus alpha 1 plus a2 alpha 2 x to the power again alpha 2 minus 1 plus 1 makes it alpha 2 y to the power 1 minus. So this is x times del z by del x. Okay, and similarly, let's find del z by del y. That's the partial derivative of z with respect to y, treating x as a constant. That's a1 times x to the power alpha 1, 1 minus alpha 1 y to the power 1 minus alpha 1 minus 1 plus a2 x to the power alpha 2, 1 minus alpha 2 y to the power 1 minus alpha 2 minus 1. This is how I calculate the partial derivative of z with respect to y, treating x as a constant. So I get a1 times 1 minus alpha 1 x to the power alpha 1 y to the power minus alpha 1 because 1 and minus 1 cancel out plus a2 1 minus alpha 2 x to the power alpha 2 y to the power 1 and minus 1 cancel out minus alpha. This is del z by del y. Now I'm going to multiply del z by del y further with y. So let us see what do we get. So I'm going to erase the initial part off. And let's figure out what we get as y times del z by del y. So y times del z by del y is going to be this whole expression del z by del y. I multiply this by y. So it's a1 1 minus alpha 1 x to the power alpha 1 y to the power minus alpha 1 times y plus a2 1 minus alpha 2 x to the power alpha 2 x to the power alpha 2 y to the power minus alpha 2 further multiplied with y. So this is going to be a1, 1 minus alpha 1, x to the power alpha 1, and y into y to the power minus alpha 1 is y to the power 1 minus alpha 1 plus a2, 1 minus alpha 2, x to the power alpha 2, y to the power 1 minus alpha. This is what I get as y times del z by del. Okay, so we have got x times del z by del x. This is x times del z by del x. And this is y times del z by del. Now all I have to do is add them up. Okay, so let me do that. Let me first of all, erase this portion off. Students should have written down the question. You should have covered up what we have covered till now. So let's, quickly add x times del z by del x and y times del z by del y. If I erase all this off, I can say therefore x times del z by del x plus y times del z by del y is going to be, so x times del z by del x is this whole expression a1 alpha 1 x to the power alpha 1 y to the power 1 minus alpha 1 plus a2 alpha 2 x to the power alpha 2 y to the power 1 minus alpha 2 plus y times del z by del y is a1 1 minus alpha 1 x to the power alpha 1 y to the power 1 minus alpha 1 plus a2 1 minus alpha 2 x to the power alpha 2 y to the power 1 minus alpha 2. Now if I solve this, therefore x times del z by del x plus y times del z by del y is going to be, now let us see what all we can take common. So within this expression and this expression, I can take a1 x to the power alpha 1 y to the power 1 minus alpha 1 common. So inside the bracket, I get alpha 1 plus 1 minus alpha 1. And within this expression and this expression, I can take a2 x to the power alpha 2 y to the power 1 minus alpha 2 common. So inside I get alpha 2 plus 1 minus alpha. Okay, so alpha 1 minus alpha 1 cancel out, alpha 2 minus alpha 2 cancel out. What do I get if I erase this particular part off? I get, therefore, x times del z by del x plus y times del z by del y is going to be a1 x to the power alpha 1 y to the power 1 minus alpha 1 plus a2 x to the power alpha 2 y to the power 1 minus alpha 2, which is nothing but z. If you look at the original function, isn't this z? So I have shown that x times del z by del x plus y times del z by del y is equal to my function z. Therefore, Euler's theorem is verified. Euler's theorem is verified. So hoping all students have understood, how we have solved for this particular numerical. Okay, so let's now move forward to the next numerical for practice. Let's look at the next numerical. Let's now move to the next question, question number 2. This is based on economic application. So let's quickly look at this question. Given the following production function, given the following production function, which is f of kl equals a k to the power alpha, l to the power beta, e to the power alpha times k by l, where a, alpha, beta, a are all positive constants. They are all positive constants. And let me also make a correction here, guys. This is a. Please make a correction. This is a. So it's a, capital A, k to the power alpha, l to the power beta, e to the power small a times k by l. A, alpha, beta, and small a are all positive constants. Part A asks us compute the marginal product, compute the marginal products Fk and Fl and verify whether the Euler's theorem holds. Compute the marginal products Fk and Fl and verify whether the Euler's theorem holds. So first of all, let me solve for this particular part. How do I find the marginal product? Remember, we partly differentiate the production function with respect to the respective inputs to find the marginal product. So my Fk is nothing but marginal product of capital. It's the marginal product of capital, which is nothing but the partial derivative of the production function with respect to capital stock. So if I find del F by del K, treating L as a constant, so it's going to be A L to the power beta. And then within K to the power alpha and E A to the power K by L, I'm going to apply the product rule of differentiation. So I get K to the power alpha times E A K by L times A by L when I partially differentiate this with respect to K plus E A to the power K by L times K to the power alpha derivative is alpha K alpha minus. So see how I have partially differentiated the production function with respect to the capital stock. So A and L to the power beta are outside because they are constants. And then to K to the power alpha times E to the power A times K by L, I apply the product rule of differentiation. We all know the product rule, right? K to the power alpha times the derivative of E to the power A times K by L, which is this whole term, plus E to the power A K by L times the derivative of K to the power alpha is alpha K alpha minus 1. So I can write Fk finally as, it's going to be A L to the power beta times A to the power K by L, A to the power K by L times K to the power alpha by L, okay, plus alpha A to the power K by L times K to the power alpha minus. Okay, now I can take something common. I can take E to the power A K by L as common. So I get A L to the power beta, E to the power A K by L. This is common. Inside the bracket, I get A K to the power alpha by L, K to the power alpha by L. Okay, plus then I have alpha K to the power alpha minus. Okay, this is what I get when I take E to the power A K by L as common. So I hope students are clear till here. Then let's find out FL. FL is going to be called the marginal product of labor. This is the marginal product of labor. Mathematically, it's del F by del L. That means we are now going to partially differentiate the production function with respect to labor, treating capital as a constant. So A K to the power alpha is a constant. And now I'm going to apply the product rule to L to the power beta times E to the power AK by L. So it's L to the power beta times the derivative of E to the power AK by L is E to the power AK by L times minus AK by L square, if I differentiate with respect to labor, plus EAK by L times the derivative of L to the power beta is beta L beta minus 1. This is what I get as Fn. Okay. Now let me erase the initial part completely. I'm erasing the question of, let's work out FL, simplify it further on the top. So if I calculate, if I simplify FL now, it's going to be, so I can again take E to the power AK by L as common. So I get A K to the power alpha, E to the power A times K by L. This is common. Inside the bracket, I get L to the power beta times minus AK by L square plus beta L beta minus. This is my FL. Okay, and now I leave it as an exercise for all students. You can verify the Euler's theorem on your own. What do you need to do for the Euler's theorem? For the Euler's theorem, all you need to do is find k times fk plus L times f and verify that it's equal to the function f of kl. Now, this is something I leave it as an exercise for all students. You should be able to verify the Euler's theorem on your own now. That is not difficult. Okay. So basically, the main thing was to find out the marginal products Fk and Fl using the concept of partial derivatives. So Euler's theorem is what students can verify yourself. Just multiply Fk expression with K and just multiply the FL expression further with L and add them up, solve the algebra part to get it exactly equal to f of k. Okay, now the next part of the question asks us part 2. If I erase this part off, let us see what part 2 is asking. So I'm erasing this part off. I'm erasing this part off. Let's look at what part 2 is asking us. If it is required, that Fk and Fl both should be positive, what restrictions should be imposed? What restrictions should be imposed on the range of values of Kn? What restrictions should be imposed on the range of values of Kn? Okay, if you want Fk and Fl to be strictly positive, what should be the restrictions we should impose on the values of Kn? Okay, now when will Fk be positive? Let's look at Fk. So this is my expression for Fk. Now students can clearly see that A is positive, L is positive, E is positive. For Fk to be positive, the term inside the bracket should be positive. That means I can say that this term should be positive. So I can write that for Fk to be positive, A k to the power alpha over L plus alpha k alpha minus 1 should be greater than 0. Okay, and if I take something common, let me take k to the power alpha minus 1 common. So this implies k to the power alpha minus 1 times I get a k by L plus alpha. Within this expression, guys, I've taken k to the power alpha minus 1 common. So inside I get ak by L plus alpha. This should be positive. Now k to the power alpha minus 1 is always positive, because capital stock cannot be negative. So that means the term inside the bracket a k by L plus alpha should be positive, which implies a k by L should be more than minus alpha. Alpha I take to the right hand side becomes minus alpha. So I can say that my capital to labor ratio should be more than minus alpha by E. This is the condition for Fk to be positive. I can write this is the condition for Fk to be strictly more than 0. I'm repeating again, Fk is nothing but this whole expression should be greater than 0. I can take k to the power alpha minus 1 outside the bracket. So inside I get ak by L plus alpha. Now k to the power alpha minus 1 is anyways positive. That means the term inside the bracket ak by L plus alpha should be positive. Take alpha to the right hand side becomes minus alpha. K by L should be more than minus alpha by L. Remember, a goes here in the bottom. Similarly, what is the condition for FL to be positive? Now FL is something which students can see on the top of their screens. If I erase this part off, erasing this part off, Students can now see the FL term on the top here. So I can say that for FL to be positive, it implies A is positive, K to the power alpha is positive, E to the power AK by L is positive. That means the term inside the bracket should be positive. That means L to the power beta times minus AK by L square plus beta L beta minus 1 should be positive. Okay, so if I now let me take something common here. Let us see what we can take as common. Again, I can take L to the power beta minus 1 common. So I get minus AK by L square times L, because I've taken L to the power beta minus 1. So here I'll get L plus beta. Should be more than 0. L to the power beta minus 1 is anyways positive because because L is a positive number and beta is also a positive constant. Okay, so this is positive. That means this implies that this term inside the bracket should be positive. That means minus AK. This L cancels with the power here, so it becomes minus AK by L plus beta should be positive, which implies beta should be more than AK by L, which implies beta by alpha should be more than K. This is the condition for FL to be positive. So that means my capital to labor ratio should be less than beta by alpha for the marginal product of labor to be positive. So these are the conditions. The students should be very good with, solving inequalities. In order to solve these kind of problems, it should be good with the algebra part and inequalities. What we have just done is, we started with the inequality Fk more than 0. We solved it to get K by L more than minus alpha by A. We started with the inequality Fl more than 0, and we found out that this is satisfied only when K by L is less than beta by alpha. So hoping all students have understood this. And then let's look at one last particular question for this particular lecture, again based on the concept we do in macroeconomics. Let's look at question number 3. For constants, A, alpha and beta, the gross national product which in macroeconomics we also call as GNP, in year T, that is YT, is related to the real capital stock KT and the labor supply LT as follows. Okay, so we are given that Y of T is equal to A e to the power alpha T times K of T to the power beta, L of T to the power 1 minus beta, where we are given that A and alpha are positive and beta lies between 0 and. Okay, so for the constants A, alpha, and beta, we are given this expression for the gross national product in year T. YT is related to the real capital stock KT and the labor supply LT as follows. Okay, A and alpha are positive, beta lies between 0 and 1. Okay, so the question asks us find an expression for the proportional rate of growth. Find an expression for the proportional rate of growth of GNP in terms of the constants, and the proportional rate of growth and the proportional rates of growth of capital stock and labor supply. Okay, this is what the question is asking us. We need to find out an expression for the proportional rate of growth of output, proportional rate of growth of output or GNP in terms of the constants and in terms of the growth rates of capital and labor respectively. So how do we start this? So remember my lectures on proportional rate of growth and elasticity. I have covered this in my mathematical methods for economics part 1 course. In my basic mathematical methods for economics MME 1 course, I have covered how to find out proportional rate of growth and elasticities. You first of all, the first step we do is we take logs. So consider y of t, which is a e to the power alpha t, k of t to the power beta, l of t to the power 1 minus beta, taking logs on both sides. I get log yt is equal to log of this whole expression a e to the power alpha t, kt to the power beta, lt to the power 1 minus beta. This implies log of yt is equal to, if I open up using the rule, log of a product is the sum of logs. So this is log a plus log e to the power alpha t plus log kt to the power beta plus log lt to the power 1 minus beta, which I can write it as log of yt is equal to log of a plus alpha t comes down log e plus beta times log kt plus 1 minus beta log lt. We have used properties of logs. Okay, so log e is equal to 1. We all know that. So if I erase this initial part off, I can continue with the last equation. I can write that therefore log of yt is equal to log a plus alpha t times log e, but log e is 1, so I am left with alpha t plus beta times log of kt plus 1 minus beta times log of L. Now let's differentiate the above equation with respect to time. Because to find the growth rates, we differentiate with respect to time because it's the change in the variable over time. So differentiating the above equation, with respect to time, which is t, I get 1 over yt times the derivative with respect to y, the derivative of y with respect to t is dy by dt is equal to log a derivative is 0 plus alpha t derivative with respect to alpha t, the derivative of alpha t with respect to t is alpha plus beta times log kt derivative is 1 over kt times dk by dt plus 1 minus beta times log lt derivative is 1 over lt times dl by dt. This is what I get. And now students who have attended my mathematical method for economics part 1 course, recall from my lectures on proportional rate of growth and elasticities, this is nothing but the proportional rate of change in y. Ry is the proportional rate of change in y, which is nothing but dy by dt divided over yt is equal to alpha plus beta times this is the proportional rate of change in capital stock plus 1 minus beta times this is the proportional rate of change in labor. So I can write this is the proportional rate of change in y. This is the proportional rate of change in k. And this is the proportional rate of change in L. So I get Ry is equal to alpha plus beta Rk plus 1 minus beta R. So I have expressed the proportional rate of growth of GNP as in terms of the constant, in terms of the proportional rate of growth of capital, and in terms of the proportional rate of growth of. This is what I had to show. So I stop in this particular lecture. I hope all students attending this lecture have enjoyed this particular practice lecture. Okay. So in the next practice lecture, I am going to solve problems on total derivatives, practice problems on concept of total derivatives. So we are going to look at problems on differentials and total derivatives. This is what I'm going to cover up in the next lecture. So I stop in this lecture. I hope students have enjoyed this practice lecture. Any doubts? You can unmute your mic and ask, or you can get in touch with me for doubts on call or WhatsApp, or you can mail me your doubts at divineschoolof economics@gmail.com. This is where I stop in this lecture.